An apple once detached off of a tree, and the earth fell towards it. We all know Newton's laws of motion and his universal law of gravity, but do we really know their implications? Let's go through the laws of motion and see why almost everyone misunderstands the third law of motion. Imagine having this U-shaped ramp. A ball let off from this height would roll down and reach the same height on the other side if there was no resistive forces like friction and air drag acting upon it. If we were to replace the ramp with a ramp that looks like this, we would see that the ball travels a larger distance but still keeps traveling till it reaches the same level at which it was released. So if we were to make the ramp straight like this, the only logical conclusion is that the ball would continue rolling forever as it will never reach that height again. This thought experiment is in fact Newton's first law of motion. A body at rest will remain at rest and a body in motion will remain in motion until an external force is applied to it. This is often called the law of inertia. This law can be used to reason out why planets rotate for so long and why objects in space seem to be in perpetual motion all the time. Inertia is the inherent property of any object that resists the change in motion. It is generally dependent on the mass of an object. Heavier masses would require more external force to get it to start or stop moving. However, when we come to moving objects, the resistance to motion depends on the mass, but the amount of force required to change the motion differs based on the speed at which it is traveling as well. So, we define another quantity that determines the amount of continuous motion present in an object, which we call momentum. It's generally formulated like this, as the product of the mass and velocity. However, we'll cover other forms of momentum in special cases like massless particles of photons in another video. This now brings us to Newton's second law of motion. Generally, it is described like this. The force acting upon a body is equal to the rate of change of momentum. Remember how a force acting upon the body was required for it to change its state of motion? Imagine having this object moving at 5 meters per second, and it needs to be stopped within a certain amount of time. As we start applying a force in the other direction, the velocity would slowly reduce till it became zero. The greater the force, the faster the momentum would reach zero. That is why we can state that the force applied is equal to the change in momentum divided by the time it took to change the momentum. The reason we have to use momentum and not just velocity is because a greater mass would require a greater force to get the object to slow down in the same amount of time. However, when we write the equation of force, we can see that velocity divided by time is nothing but acceleration, and hence we can write F is equal to ma, which is the most commonly seen expression for Newton's second law. With this, we finally come to Newton's third law of motion. Every action has an equal and opposite reaction. Although this is arguably the most famous of his equations, this is the one that is actually very tricky and almost everyone gets wrong. Action has a precise definition in physics. However, we tend to keep this law specific to forces. This law means that every force comes in a pair where the other force is equal and opposite. Let's take for example this apple placed on this table that is placed on the surface of this planet. We all know that a planet exerts a gravitational force on the apple, pulling it downward. From Newton's second law, we can calculate that the force is equal to the mass of the object times the acceleration due to gravity, often written as mg. Now, most people will say that there is no motion in the apple due to Newton's third law, which provides the normal reaction force from the table onto the apple. However, this is where it gets tricky. If we think that the reaction force is the force applied by the table on the apple, then the reaction force disappears if there was no table and no equal and opposite force exists, hence defying Newton's third law. In reality, the normal reaction force from the table on the apple is a consequence of Newton's first law. As the object is in rest and remains in rest, there must be no net external force, and hence the reaction force from the table must be present. But if that is the case, then you might wonder, what is the actual equal and opposite force that is spoken about in Newton's third law? In this scenario, we see that just as the planet is pulling down on the apple pulls on the planet as well. This force would be exactly equal to the same mg that was acting on the apple. This is because the mass of the planet might be much greater than the mass of the apple, but the acceleration due to gravity of the apple would be far lower, making the product of the mass and acceleration the same. So the equal and opposite reaction of the force applied on the apple by the planet is the force applied by the apple on the planet. Now, the curious minds will be wondering about the normal reaction force of the table on the apple. Where is the equal and opposite reaction to that force? Similar to the force pairs of the apple and the planet, the equal and opposite reaction of this force would be the force applied by the table onto the surface of the planet. In most textbooks and literatures, this force is never spoken about, and neither is the force of the apple on the planet. Although the equations and math works out in most cases, it simply isn't the right explanation. To substantiate why considering the force of the table on the apple as the equal and opposite reaction force of the weight of the apple is not the right explanation, let's take a look at this slightly modified scenario. In addition to the previous setup, there's this additional fishing line or string attached to a solid surface, which is providing, let's say, 3 newtons of tension force in the upward direction, while the weight of the apple was 5 newtons in the downward direction. The action here is still the force of gravity on the apple, which is mg, which we've stated as 5 newton. However, the force of the table on the apple is now only 2 newtons, as the rest is balanced by the tension in the string. Based on the law, there should be only one equal and opposite reaction force. Yet, there are 2 forces acting at different points of different values. This becomes even more complicated if the string was attached in this fashion. The correct explanation, however, is that the action is the weight of the apple and the reaction is the weight of the earth on the apple. The reaction of this force on the apple by the table is the force of the table on the ground. Finally, the reaction of the tension force created by the apple is the tension force created by the solid surface to which it is attached. When an apple falls to the ground, the apple also pulls the earth along with all of us on it up towards itself. When we do the math, we see that it is a negligible amount, less than the width of a proton, but it exists nonetheless. Every time we throw a ball up and catch it, we actually push the entire earth down and the ball pulls the entire earth back up while falling. So the next time you drop your phone, remember, you just made the entire earth fall as well. Thank you all for having enough inertia to watch this far into the video. I really hope you learned a little more and gained some intuition about the 3 laws of motion. If you know anyone who probably has the same misconceptions or who might gain by watching this video, don't forget to share this video with them as well. We will be coming back with videos explaining more misconceptions about mass, energy, and momentum, and we'll go into more details about Newton's laws of gravity and how they hold up with Einstein's theories as well. Till then, check out PhysiFacts on Instagram if you haven't already. And until next time, stay tuned, stay safe, keep learning, and stay curious.